All right. So in last week we talked about liquids and solids, and in their their pure state. Now we're going to talk about solutions. So remember back, maybe it was last semester, we talked about mixtures. We cover that topic, mixtures. You have pure substances, and two or more pure substances together would constitute a mixture as long as there was no reaction, and the pure substances, well, actually technically you can put two mixtures together, but we're going to keep it simple. Two or more pure substances together makes a mixture as long as they don't react to produce substances with a new identity. So as long as they remain intact in the mixture, you can have homogeneous mixtures or heterogeneous mixtures. And that just has to do with the composition. If the composition varies throughout, that's heterogeneous. If it's uniform throughout, the ratio of the components, then you have a homogeneous mixture, and that's also called a solution. So you can have various types of solutions based upon their states. You could mix gases together. Right? And remember, anytime you mix two or more gases together, you always get a solution, homogeneous mixture. That's primarily because there's lots of room in there for everybody. The molecules are so far apart, and they don't interact with each other to a significant amount, then you can put as many gases together as you want and get a solution every time. In fact, we're breathing a solution now. Primarily 78% nitrogen, 21% oxygen, and about 1% argon with some trace. You can mix two liquids together, make a solution, right? All kinds of booze, or ethanol, water, and some other stuff. Antifreeze is a solution of a liquid in a liquid. Ethylene glycol and water. It's usually in your engine, it's usually 50-50. And that's one thing you want to keep away from your dogs, because it'll kill them. Antifreeze, ethylene glycol tastes sweet, and dogs have a sweet tooth. Brass is a solid in a solid. You mix copper and nickel together. Of course, you have to melt them first for them to mix, but once they're re-solidified, now you have a solid solution. Carbonated water is a solution of a gas, carbon dioxide, in water. So that's what causes the fizz when you crack the cap on a bottle of pop. Seawater. This is seawater and sugar water. Those are what we normally think of as solutions, where you dissolve a solid in a liquid, and after they're dissolved, you have a liquid. How do we know that it's just a mixture? You can recover the components by physical means. For instance, if you want to get the salt back from seawater, or the sugar back from making your bird feeder juice, you just evaporate the water. And for the bird feeders, you've got sugar left over. Put sugar in, you get sugar back. The identity of the substances has not changed. Here's an odd one. A solid, a gas solution in a solid. So and the example here is hydrogen and platinum. When some companies produce partially hydrogenated oils, and they do that because it raises the smoke point and it raises the melting point. Makes them more useful for restaurants. Unsaturated oils typically have a lower smoke point and a lower melting point. They're healthier for you, but because when you hydrogenate a fat, an unsaturated fat, by this method where you use platinum as a catalyst and hydrogen as the reactant, the hydrogen inside the molecule, you have a double bond with a carbon here and a carbon here, and then you have stuff here and stuff here and stuff here and stuff here. What happens is, typically, I shouldn't do it that way. I should do it this way. Typically, you have a hydrogen there and a hydrogen here, and then the rest of the molecule there and there. That's called a cis bond. In popular media now we hear cis and trans. This is not the same thing. Trans would be the hydrogen's over here and the rest of the molecule goes that way. But the naturally occurring fatty acids in fats are all cis in their unsaturated form. But when you hydrogenate them with this hydrogen and platinum, it moves the hydrogen over here and over there and gets rid of that bond. And those types of molecules are not good for your health. So that's why partially hydrogenated vegetable oils are frowned upon. And more businesses are shying away from them because it's bad publicity. But those are all different kinds of mixtures. Well, since mixtures are composed of solutions, I should say, we're focusing on solutions. Since solutions are composed of a usually at least one major component, which is the solvent, and one or more minor components, which is the solute, then we need a way to express what is their concentration, because characteristic of mixtures is that the composition can change. You could make your sugar water for your hummingbird as a cup of sugar and a cup of water, which is typical. But if you want to make it more concentrated, you can put more sugar in it. In fact, you can put more sugar in there until you have substantially more sugar than you do water. So sugar is just that soluble. But we need a way to express the concentrations, be accurate about how much solute is in the solution relative to either the total amount or relative to the solvent amount. So these are four of the most common ways. The first is molarity. Molarity is, that's my abbreviation for moles. It's moles of the solute per liter of solution. So it's a whole, so if you know a number for the molarity and you know that you have in your possession 1 liter of that solution, then it will have that many moles of solute. So it's convenient, very convenient to use this measurement. It's used widely for 2 reasons. One is that possessing a certain volume guarantees that you have a certain number of moles of the solute. And the other is we use moles of solute. That way we don't have to deal with the differences in molar mass for different solutes. Because very often the behavior of a solution of a certain molarity is dependent upon not what's in it, but how much of it there is, how many moles of the solute there happen to be there. Another way is mass percent. Remember, if I haven't said before, percent is hard to deal with because it just means parts per 100. It doesn't say what those parts are. So mass percent does specify, let's see, percent by mass. That does specify that you have grams of solute per 100 grams of solution. Yeah, solution. Or you can say grams of solute per grams of solution times 100. Another one is mole fraction. Mole fraction is very useful when we're talking about gases. Mole fraction, and often you'll see the that curly QX stands for mole fraction, is equal to the moles of solute per total moles. Of everything that's in the solution. So what that does is it says the value is always less than 1. If you get a value that's 1, that means it's not a solution anymore, right? Because the total is the same as the solute, then it's all solute. And molality is the last one. That, unlike the big M, we use a little m for molality. And molality is like molarity, it's moles of solute. But we change the denominator, not liters of solution, but kilograms of solvent. Okay, we're going to use that one next week in our lab, this one right here. The advantage to using this one over that one as an expression of concentration is, notice when we're dealing with volume, it's susceptible to temperature change. If you increase the temperature, then your volume will increase. And if we're investigating in that lab, for instance, if we're investigating freezing point depression, freezing point, that's temperature. We want to measure a concentration that does not respond to temperature. So that's why we use this one. It's moles of solute per kilogram of solvent. Right? There's nothing in there that will respond adversely to temperature. Those are the most common concentration units. And I already told you that. Oh, here we have a problem. Okay. Calculate the molarity of a solution that has 1 mole of sugar and 125 milliliters of final solution. So if we've got 1 mole of sugar and 125 milliliters, there's the catch. Wrong units. It has to be liters of solution. So how many liters is 125 milliliters? Well, if you work with a lot, you know that you just need to move the decimal place 3 places to the left. So it's 0.125 liters. Or if you want to use the prefix method, what does milli mean? Milli means 10 to the minus 3. Okay, that's what this is right here. Times 125. So 1,000 or 1,000 divided into 125 is 0.125 liters. So that's what we need in the denominator. So we divide 0.125 into 1, and that should be 8, I think. Yep, 8 molar. Let's see, just erase these now. Probably going to have another one with molarity in just a second, so I'll leave that one up there. Let's say you have 10 molar sugar solution, 10 molar. Yeah, here we go. 10 molar sugar solution. What volume of this solution do you need to have 2 moles of sugar? Well, if we simplify this equation and we say M equals moles divided by volume, recognizing that volume has to be in liters, then we got this one, and we've got this one, which is part of the question. Now we're going to solve for that one. What volume do we need to guarantee 2 moles of that? So you can plug in the values you know and solve for the unknown, or you can solve for the unknown. like that. And then plug in the values. So we know this needs to be 2 and this needs to be 10. This is molar and this is moles. So 2 divided by 10 is what? 0.2, 3 significant figures. And this is liters. So 0.2 liters or 200 milliliters. That's the volume that you need to, say you have a 10-liter container with this concentration. If you take out 0.2 of a liter from it, then you know that you will have 2 moles of sugar. That's what that means. All right, here's another one. It just gets curiouser and curiouser. How would you calculate the molarity of a solution if you only know the mass of the compound and the final volume? Well, you need moles, right? So you'd have to take the mass of the compound and work out the number of moles that you possess at that given mass. In this case, we've got 100 grams of sodium hydroxide. 100 grams of sodium hydroxide. We also want to make a separate solution of 100 grams of potassium chloride, correct? Yeah. And the final volume will be 250 milliliters. Okay. So we would convert this to liters. 0.2500 liters, but these have to be converted separately into moles. So we use a little dimensional analysis here, and grams on the bottom, moles on the top. So what's the molar mass of sodium hydroxide? Okay, let me see. Sodium is 23. Oxygen is 16 and hydrogen is 1.01. So that's 40.01. Okay, so we just say divide that into 100 and we got 2.499 moles of sodium hydroxide. How about potassium chloride? Potassium is 39.10 and chlorine is 35.45. So that's 5 here for 74.55. Okay. So divide that into 100. I get 1.34. 1.341 moles of potassium chloride. So I think you can see where this is going. If they've got the same volume, final volume, you've got fewer moles of potassium chloride, even though the same mass, fewer moles, this concentration is going to be less molarity than that one. And all we have to do is say for this one, we'll say 2.499 moles divided by 0.2500 liters. Let's see, swap that one. And I get 9.997 or 10. Let's see. How many significant figures? 9.998. I think the slide is going to say 10. Molar. And this one's going to be 1.341 moles are the same volume. We're making separate solutions. 1.311 divided by 0.25. 5.366 molar. All right. Yeah, I was right. They rounded off to 3 significant figures. Actually, should be able to keep 4. And then potassium chloride is 537. They rounded off to 3. So the point we're trying to make here is that mass is not moles when you're calculating concentrations. Mass percent. All right. Mass percent is really very useful. In the first place, it does not vary with temperature because there's no volume term in there anywhere. In addition, calculating mass percent is useful, particularly useful because all labs have balances. Right? You can measure mass easily. So it's a good place to start. What's the percent by mass concentration of glucose in a solution made by dissolving 5.5 grams of glucose in 78.2 grams of water? So we have 5.5 grams of glucose and 78.2 grams of water. So the mass percent would be the solute on top. I can do better than that. What's the total mass? Have to sum them together, don't we? Plus 78.2 grams times 100. Okay. And I'm going to let the slide tell us what the answer is. 6.6% by mass. And when you write it like that, if you just slap that up and nobody knows where it came from, you would be advisable to say mass, mass. That way there's no mistake. Mole fraction. We covered that one. Moles of solute per total moles. So a solution of phosphoric acid was made by dissolving 8 grams of H3PO4. 8 grams of H3PO4 in 100 milliliters of water. 100 milliliters of water. And we want to know the mole fraction. Let me see. Okay, I don't work it out on the slide, so I need to do it by hand here. Okay, if we're looking for mole fraction of H3PO4, we need, like the formula said, moles of H3PO4, total moles of solution. Right. So how many moles are total in the solution? Well, once we find the moles of this and the moles of that, that becomes the denominator. So this one's easy. We just need the molar mass of H3PO4. Right. So 3 hydrogens is 3.03. Right. Phosphorus. Phosphorus is 30.9. I need a smaller, closer chart. Unless you guys have one, Jenny, tell me what it is. Here it is. Phosphorus. 30.97. And then 4 oxygens, right? So that's 16 times 4 is 64. 98.00. There we go. So this will tell us the number of moles of H3PO4. Let's see. 8. 8.16 times 10 to the minus 2 moles of H3PO4. How about moles of water? We don't have a conversion factor for milliliters of water. That's why they told us that the density of water is 1 gram per milliliter. So if you have 100 milliliters of water, how many grams do you have? 100 grams. You remember the molar mass of water? 18.02. 16 plus 2.02 for the hydrogens. So we divide that into 100. 5.549. That reminds me of. You ever watch Hee Haw? Old episodes. What was it the Junior Samples used to say about the telephone number? Call BR549. Coincidence. Okay, so this is the total moles. We'll go ahead and add this one to that for the total. Right? This will be in the numerator, times 10 to the minus 2. What is that in standard notation? 2, 1, 2. So 0.0816. 0.0816, right? 2 places, 1, 2. So this will be the total. Let's see, I got them lined up wrong. I do have them lined up wrong. This is 6. This is 10. 1 12 is 13. 6, 5. This is 5.6306 equals. And it's going to be a decimal fraction. Let's see, let's flip this one. And 5.6306. Strictly speaking, that's not kosher, because I didn't use my add subtract rules for significant figures. But we'll get close enough to find the answer. And divide that into it. This is, let me put it in standard notation. 0.0145 mole fraction for H3PO4. Okay. And like I said before, mole fraction is always less than 1. Plus, if you have accounted, if there's more than one solute in there, and you're doing mole fraction for each one, then add up all the mole fractions of each of your components plus the solvent, and that should be 1 within calculation errors. It might be 0.9999 or 1.00001, something like that, but it'll be really close to 1 if you have counted for everything in the solution. Then you add them up and they should be equal to 1. Molality. All right. This is the one that we're going to be using. Molality, little m. I should have left that stuff up there. Now I got to calculate it again. 8 grams of H3PO4 in 100 milliliters of water is what molality? All right, so let's do it again. H3PO4. That's 3.03 plus phosphorus 3097 plus 64. $98. So if we've got 100, is that right? 100 grams? Yeah, no, 8 grams, excuse me. 8 grams of H3PO4. And we're going to convert that 98 grams per mole. And that's equal to 8 divided by 98. 8.163 times 10 to the minus 2. That's how many moles of phosphoric acid we have, H3PO4. Okay. Now for this one, we've got 100 milliliters of water. Right? We know that that's 100 grams, right? I put too many decimal points. Grams of water. How many kilograms is that? Because that needs to be in the denominator. This goes in the numerator, 8.163 times 10 to the minus 2. And in the denominator, we need kilograms of solvent. Right? 100 grams is 0.1 kilogram, isn't it? Okay. 1, 2, 3. 0.1 kilograms. Right? So if you divide by a tenth, that's multiplying by 10. So it's 8.163 times 10 to the minus 1, 1, or 0.816. I better stop there. Molal. Okay. And that just means moles of solute per kilogram of solvent. All right, so that's the practical expression of concentration for different types of solutions. Now we're going to talk about the theory behind what's actually happening when a solution forms. I erased that too soon. Okay. So when a solution forms, remember I've always said, probably getting tired of hearing it, nature just does what it does. And we try to explain why. This is definitely one of those cases. When you put a solute into a solvent and it goes into solution, 3 things are happening. And from the solution's viewpoint, it's all happening at once. But we're going to separate it into 3 processes so that we can try to wrap our brains around it. So when you form a solution, 3 things can happen. 3 things do happen. One is the solute. The solute breaks intermolecular bonds. Right. Solutes, there's some type of interaction that's holding those solute molecules together. If it's a solid, they're pretty strong. If it's a liquid, they're just a little bit weaker. If it's a gas, of course, they're almost non-existent. But when you do that, you have to put energy in. So this is an endothermic process to get those solute molecules apart. The second thing that's happening simultaneously is the solvent. You have to break bonds here also. Okay, that's another endothermic process. Sometimes it's described as making holes. We're making holes in the solvent for the solute molecules to fit, but they're both endothermic. Then when the solute molecules and the solvent molecules come together, then you get the third process. And here you establish solute solvent bonds. And this one is exothermic. You get energy back. In this one, you put energy in. This one, you put energy in. And this one, you get energy back. Now, we know from practice that when you form solutions, sometimes it gets colder and sometimes it gets warmer. Okay. And the explanation for that is, what's the balance between these two processes and this process? If you put a lot of energy in here, here, and here to get those molecules apart, but you don't get much back, then the process is going to be endothermic, right? The balance is toward the endothermic. It's going to get colder, right? And cold packs that they have in the hospital, plastic bags with a little capsule inside. It's water and something inside the capsule. Break the capsule, mix it up, and it gets cold. That's what's happening. It takes a lot of energy to break the solute apart and a lot of energy to make the holes, and you don't get much back when the associations are formed. The other way around, if you break the pack and it gets warm, that means it took a little bit of energy here and a little bit of energy here, and you get a whole lot of energy back when it reforms the bonds between the solute solvent. All right, and there's an expression for it. In mathematical terms, this would be delta H1. This would be the enthalpy 2, and this would be the enthalpy 3. When you add them all together, the sign on the delta H of the solution determines whether it's endothermic or exothermic, right? If it's endothermic, right, it's always in perspective of the system. So the system says if you're putting energy into it, that's a positive value. That's a positive value. This is a negative value. Exothermic means negative value. Remember thermochemistry? So when you just put them in a line and add them together, then if this negative is bigger than these two positives together, then it's exothermic. You know, as a practical mathematical operation, that's the expression. If these guys are huge positive values and this one's a tiny negative value, then the overall is positive and the process is endothermic. Okay. That slide just says what I told you already. I'm not going to spend any time on it. Enthalpy of solution is what we call that, heat of solution. And this is a energy diagram that basically says the same thing. On the left-hand side, the delta H3 on the right, you get a lot of energy back. So that's the exothermic side is on the left. The endothermic overall is on the right, because you put a lot of energy in and you only get a little bit back. So that's the cold pack. Okay, can we explain why water and oil don't mix? Let's see. Is there an explanation for that, or do I need to? Do I need to expound? I need to expound. Think about it. If, let's say this is oil, and the solvent is water, right? Or it could be vinegar. You're making a salad dressing. I do. Put a little oil in vinegar in those little jars with the blue caps on them. After you make your SOS with Armor chipped beef, then you clean them out, and they make great salad dressing containers. You just put a little oil, a little vinegar, however much you want, and then I throw some Mrs. Dash in there for flavor, and just shake it like crazy, and then pour it on your salad before it separates. Okay, so what's happening in here is oil. What are the forces between the oil molecules as a solute? Oil is nonpolar, correct? So the only forces you have here are London dispersion forces. Okay? For water, and that takes very little energy. It's a small input, right, to get those apart. Water is hydrogen bonding, right? It takes a lot of energy, large, right? Okay. And what kind of interaction do you have down here? The only kind of interaction you have available, since this is nonpolar and that's polar, the only interaction you have down here is London. So it's very weak, small value. Okay. So, what was the question? Explain why water and oil don't mix. Well, we've separated these, and at room temperature, there's not enough energy to separate those. Right? When you mix them together, unless you've got put a lot of energy in which we don't at room temperature, that means room temperature, maybe we can get these apart, but we can't get those apart. We can't make any holes. We cannot get these apart. So any energy you get back here is not enough to overcome those bonds. So they don't mix. They don't interact at all. Their interaction is insufficient to overcome the hydrogen bonding. Okay, so with that in mind, let's look at this chart, and we see that the left-hand column says solute solvent, polar solute, polar solvent. Second one is, and then let's see, third one down is nonpolar solute, nonpolar solvent. And then in between, you have the second one is nonpolar solute, polar solvent, and polar solute, nonpolar solvent. Okay, so what does that say about the delta H's here? Well, for the first one, where you have polar and polar, if this is polar, now let me remove that so it doesn't muddy the water. We're talking about a different scenario now. There we go. So if these are both polar, polar and polar, this takes a lot of energy to separate these solute molecules. This takes a lot of energy. So it's very high endothermic process for both of these. But when they interact down here, you get a lot of that back. Right? The polar and polar, they interact very strongly. So the overall delta H for that solution is very small, because you put a lot of energy in, you get a lot of energy back. So the enthalpy of solution is small, and a solution tends to form because they're both polar. What if they're both nonpolar? And it takes a little bit of energy to overcome London forces, a little bit of energy to overcome these London forces, and you get a little bit of energy back. So in that case, you do get a solution. And again, the delta H is very small because the difference between them is very small. Those solutions are predicted. They're very likely to form. Non-polar solute and a polar solvent is the one we discussed with oil and water. Right? So we don't have to hammer that one anymore. But what if it's reversed? What if you have a polar solute and a non-polar solvent? A lot of energy required here, not much energy required here, and you get very little back. It's a large positive input that's required. And at room temperature, there's not enough energy to do it. Okay? Now, perfect case in point. Have you ever seen a dirty engine, an old engine, steam cleaned? It's fascinating. You got this guy with protective, big gauntlet gloves on and a heavy coat, and he's got this line coming from a steam generator, and it goes through his magic wand, and he pulls the trigger, and it blasts. It's like when you go to a car wash, where people are there and they spray down your car before you drive through the wash. Except his wand has steam coming out of it, not just pressurized water. So it's very, very hot, very high energy. So with that being said, what happens when that steam coming out of that nozzle hits the oil on the engine, the dirt in the oil? It does two things, of course. It increases the temperature of the oil to melt it, make it more fluid, and it blows it off. But some of it actually dissolves in the water because there is sufficient energy with that steam wand to overcome the endothermic process that's required. Okay? And temporarily, you get a solution. Of course, when the steam cools down, when it condenses on the ground, then a lot of it evaporates and you're left with oil all over the place. Okay, we can speak of the formation of solutions and the energies involved in terms of probabilities too. If we increase the probability of the state when the solute and solvent are mixed, that favors a solution. All right, I was trying to think of an example. Increase the probability of a state. And that says the probability of, is it liquid or solid or gas? I guess any one of those states. If the probability is high for the formation of that state, then you're likely to form a solution. But if, and we've already discussed this one, if the large amount of energy is required, then the process is less likely to occur. That's not explicit in that slide, is it? No. Rule of thumb. I like rules of thumbs. If I had enough thumbs to cover all the rules of thumbs I've used over the years, I'd have 4 hands and 6 feet, all thumbs. Like dissolves like. You've heard that before, probably. Right. Polar solute and polar solvent form a solution. Non-polar solvent and non-polar solvent, solute and solvent, form solutions. But the opposites don't meet. If you got a non-polar solute and a polar solvent, or a polar solute and a non-polar solvent, you won't get a solution. That's one of the takeaways from this. So we've got several factors that we can discuss as a practical matter in terms of solubility. So we've already mentioned one of them. Polarity influences the solubility of a solute in a solvent. If there's similar polarities or a lack of polarity, then you're likely to produce a solution. And that depends on two things. Remember at the end of last semester, what two things determine polarity? Polar bonds, right? If you've got polar bonds in your molecule, then you need one other factor. If there are no polar bonds in the molecule, stop there. The molecule cannot be polar. But if you have polar bonds, then you have to consider geometry. Because you can have polar bonds, and if they're equal and opposite in some form or fashion, they cancel each other out, and you have a nonpolar molecule. So the polarity affects solubility. That's why carbon tetrachloride used to be used in dry cleaning. Right? It's very effective at dissolving oils. And when you get clothes dirty, most of the time there's oil involved, right? And usually comes off of your skin. But that attracts dirt. So if you can dissolve the oil, then you can get rid of the dirt. Only some fabrics don't like water, right? Don't like water in detergents. So those fine fabrics require dry cleaning, they call it. And they use a different type of solvent to get the oils out of them and the dirt attached to it. Carbon tetrachloride was used for years and years and years until OSHA and the EPA got hold of it. And they said, carbon tetrachloride is bad for the environment. It's bad for the workers. Can't use it anymore. So they had to find something else, right? Which is obviously more expensive. But carbon tetrachloride, remember? Carbon has a polar bond for each of them in that direction. Okay, all of them are polar. But what's its shape? Remember, the central atom with 4 groups is a tetrahedron. And a perfect tetrahedron with these equal bonds will cancel each other out. And you've got a nonpolar molecule. Okay, what other conditions can affect solubility? Well, when gases are involved, pressure is a factor, right? For solids and liquids dissolved in a solvent, pressure has no effect. But when the gases are present as the solute, then the pressure has to be considered. I'll come back to that slide in a minute. I don't want to lose this thought. Henry's law governs the solubility of gases in a liquid solvent. Actually, in a solid solvent too. But if you want to determine the concentration of a gas in a solvent, that concentration is equal to some factor times the pressure. And that constant is proportionality constant. It has to be determined for every solvent. But we can do like we did with gas laws, right? And produce, remember Boyle's law, P1, V1 equals P2, V2. We can do the same thing for this one. So if you know before conditions and some of the after conditions, you can solve for the unknown. So you can do the same thing with Henry's law too. But what you need to know is the partial pressure of the gas. What is the partial pressure above the liquid, say in the headspace? Right, you got a liquid here, and you got your gas up here. And the pressure bearing down on that surface will increase the concentration of the gas as the pressure increases. That's what that means. So as the pressure goes up, concentration goes up. And that is dissolving carbon dioxide in water makes pop, and that's why they keep them well sealed, right? When you crack the cap, it goes because there's pressure in that vessel that's keeping the carbon dioxide dissolved in the liquid. There's another discussion, actually a series of images that explain that as you increase the pressure, you're increasing the number of impacts of the gas molecules on the surface. And the number of impacts means you have that much more probability of a gas going into that solution with the increase in frequency. Temperature also affects solubility of gases. Only it works in the opposite way. As you increase the temperature of the solvent, the gas becomes less soluble. So why is that? Well, let's see. Got your liquid, got your gas molecules here, and they're moving every which way. They're moving this way. They're going all over the place. They have a certain amount of kinetic energy at a given temperature. Right? So if that's temperature 1, and there's a certain solubility here with that gas, what happens if you increase the temperature? Right? So you increase the temperature to a new temperature higher. Right? So what do you have? Well, you've got gas molecules dissolved in this liquid here, and they're responding to that temperature too. Right? They're moving faster now. So that means that they're leaving the solution faster than they're entering the solution. So we decrease the solubility of gas by increasing the kinetic energy of all the molecules, including the solvent. So practical application, if you've got a bottle of pop, 2-liter bottle of pop, and you want to preserve its fizz, don't open it at room temperature because it's less soluble that way. Put it in the refrigerator, cool it down for a couple of hours. Then you can crack the top. Instead of going, it'll go because it's more soluble. The carbon dioxide is more soluble in the pop than at low temperature than it is at high temperature. So when I was drinking pop, I don't do so much anymore. I'd bring the 2-liter bottle home and I wouldn't open it until it was cold. That's what I hate about picnics, is I always bring those room temperature or hotter, if it's in July, hotter bottles and set them out on the picnic table, and everybody's cracking them open and pouring them over ice. Well, for 2 reasons, they lose all their fizz, right? They're hot. First time you open it, they lose most of the fizz. The second is you pour them over ice, and ice makes it fizz more, right? That's a concept called nucleation sites. That's the concept behind the Mentos. Drop Mentos into pop bottles, and they explode. Right? It's the number of nucleation sites in the Mentos when you drop it in there, it causes the carbon dioxide to come out of solution really fast. Okay, enough of that. So here, and every gas has a different solubility. This is solubility in water. Well, these are not gases, I'm sorry. We've gone back to solids. Sugar is very soluble, and it increases solubility with temperature, right? That top line is more soluble. See, yeah, there it is. And potassium nitrate is a good example too. It's not very soluble at low temperature, but it increases solubility rapidly with temperature. Sodium nitrate, similar. Sodium bromide is not so soluble, is not a difference in solubility is not evident with increasing temperatures. A little bit, but not much. Potassium bromide also, and potassium chloride increase solubility. But notice the solubility of solids in, particularly salts, different types of salts, soluble in water decreases with some of them. Sodium sulfate and cerium sulfate. Those two decrease. And it's difficult to predict that they would be the ones. The common factor here is they're both sulfates. So maybe that has something to do with it. But you can't there's no theory that will predict solubility accurately. It's just a practical matter. You try it and see what happens. And that's what happens. So if we have a solution of sodium sulfate and we want to decrease its solubility, say, and drop some of it out of solution, make it precipitate, just heat it up. And some of it will come out of solution. Solubility of gases in water. Methane has a rapid change in solubility between 0 and 30 degrees Celsius. Oxygen, similar. Carbon monoxide, a little less. Nitrogen, a little less. Helium shows almost no variation in solubility with temperature. Some, but not a lot. And notice it's also the least soluble of all of those particular gases. So you'll notice that nitrogen, if we just stay with one temperature, nitrogen is more soluble than helium and oxygen is a lot more soluble. So if I prepare a solution at room temperature, then nitrogen and oxygen from the air over time will be solubilized in that solution. Practical application. If I try to use that solution in a liquid chromatograph and I put the solution under huge pressure, this high pressure liquid chromatograph, HPLC, and drive it through this tube with a packing in it so I can separate things, it's chromatography. Then on the other end where the detector is, when the pressure is released at the other end of that tube, all that gas is going to come out of solution and wreak havoc on my detector. Right? So what I want to do is get that nitrogen and oxygen out of solution before I even put it under pressure. And the way we used to do it in the lab was we would go through a process called sparging. We would take one of these little porous stones like you can see in aquaria, where you blow pressurized air through the stone and it makes little bubbles. We use one of those in our mobile phase, the one that we're going to push through the chromatographic column, and we sparge it with helium. So we put so much helium in there, it displaces all the oxygen and nitrogen in solution. And what's left is just a little bit of helium. Helium's not so much trouble for our detectors because, first of all, it's very low solubility. But it's transparent too. So it doesn't affect the wavelength absorption characteristics of the detector. That's one way to do it. The other way is to put your solution under vacuum and just suck all the gases out of it. And that's one way that's done. So if we look at compare these two before and after. A is before, where we have an aqueous solution on the right and pure water on the left. Okay. So what we see is that the evaporation, the vapor pressure, we talked about that last week, didn't we? Vapor pressure? I think we did. Yeah, we did. The vapor pressure on a solution is lower than the pure solvent. Right? So the picture on the right is a solution, aqueous solution of a non-volatile solute, and this one is pure. So the vapor pressure here is higher than it is here. And at the molecular level, what you're seeing is that this is purely evaporation and no return because it's not sealed. And these water molecules are available to now be absorbed into this solution more rapidly than that are being evaporated. So you never reach an equilibrium here. It's all one way. So all these water molecules keep evaporating until they're all over here. Now, I've done it. I've seen it happen. And it works best if you have something that's a very, very hygroscopic solute. Sulfuric acid is perfect. If you have a high concentration of sulfuric acid in the right-hand container and you let it sit there, within 3 or 4 days, all the water is gone from the left hand and it's over there in the sulfuric acid. So one thing you need to be sure of is there room enough in that beaker? It's not going to overflow. All right. So here we're talking about vapor pressure of solutions. Last chapter, we were talking about vapor pressure. What is the vapor pressure of a pure solvent, a pure material, right? In this case, we have a solution of a non-volatile solute, right? The solute has no influence of its own on the vapor pressure itself. It does affect the vapor pressure of the solvent simply because, well, 2 reasons. If you have a sealed container here and you've got a vapor pressure there for your liquid, your solvent, then you can measure the vapor pressure, right, at a given temperature. But if you put a solute in there, it's going to decrease the vapor pressure for 2 reasons. One is you've got these solute molecules at the surface. They're interfering with the vaporization of the solvent. Plus, they have a certain attraction for the solvent. Right? We talked about that in step 3. If this thing goes into solution, then there has to be an attraction between the solute and the solvent. And those 2 factors, physical interference and intermolecular attraction, restricts the vaporization of your liquid, of the solvent. Right? And this formula, this Rayleigh law, is an expression of that, and it uses mole fraction as one of its terms. So the pressure of the solution, once we've got all this stuff in here, the pressure of the solution is equal to the mole fraction of the solvent times the pure vapor pressure of the solvent. So if we calculated the mole fraction of phosphoric acid, right, it was a very small number. And since there were only 2 components in there, what's the mole fraction of the solvent? It's just 1 minus that value. So it'd be like 0.9 something. That's what you put in here. And you know the vapor pressure of the pure solvent at that temperature, plus you know the mole fraction of the solvent, that will give you the vapor pressure of the solution. Okay. That's if you have a non-volatile solute. It doesn't contribute at all to the vapor pressure, the molecules that are going into the vapor phase. Okay, and that's not every case in the world. There are solutions with volatile solutes, like booze, like ethanol and water. Both of them are volatile. In that case, this is an expression. As the mole fraction of the solvent increases, obviously the vapor pressure increases until you get 100%, or a mole fraction of the solvent is 1. That means you don't have a solution anymore. And now you have the pure solvent vapor pressure, and that's the point right up here. If you have a solution of two volatile solvent and solute, then you need a combination equation. This is modified Raoult's law. The total vapor pressure is the sum of the vapor pressure of the solvent plus the vapor pressure of the solute. So you have those two terms. Let me use this so it'll record. You have these two terms. One is the solvent and one's the solute. And the total is the sum of the two. Now, where have we seen that before? Dalton's partial pressure law? Yeah, the total pressure is the sum of all the parts. This is kind of a takeoff on that. It gets a little more complicated, but if there are only two components, the solute and the solvent, then we can talk about it at least in theoretical terms. If you look at the left-hand graph here, and you're only concerned with, let's say, partial pressure of A and partial pressure of B, it doesn't matter which one's which, then the partial pressure of A increases as the mole fraction of A increases right here. So that partial pressure increases until you get mole fraction of 1 for A, which means no more solution. Okay. You can also go backwards the other direction. As A is increasing, B is decreasing. But if B goes the other way, then B is increasing toward the left. And then this blue line is the partial pressure of B until it's the only component. And that's a pure B, and no more solution. Well, the summation is the value of this line at any point with above it this one. So if you add those two together, you get this line up here. Okay, so this is the vapor pressure line for the solution right here, connecting these two extremes right there. Now that's for an ideal solution. What do we mean by an ideal solution? We mean that, and like any ideal, this isn't reality. But if the interaction between A and B is not stronger and not weaker than either the interaction of A with itself or B with itself, right? We're not saying that there's no interaction. It's just that the intermolecular attraction here between A and B is about the same as this one with itself and that one with itself. That would be an ideal solution. And that's where you get that straight line. Now, if the interaction between the of A and B is very, very strong, then we go to the far right. And what that does is it depresses the vapor pressure of both A and B. So the summation would be this dip, this concave line. That's what you would see for the vapor pressure graph of A and B if they're very strongly interacting. If they're very weak interacting or even repulsive to a certain extent, you would get this convex right here. Okay? Nobody's asking questions, so I just assume that it's sinking in. Right, so here it is in a tabular form and with examples. So an ideal solution would be something like benzene and toluene. They're very similar to each other. So that means that their interactions of benzene, interactions of toluene are similar to the interactions of two together. Like benzene is like this. It's an aromatic compound. And toluene is like this. With a methyl group up here. Right, so it's all nonpolar and there's similar interactions this with itself, or two together, they're very similar. So that's be considered an ideal solution. The second one, where you have acetone in water, acetone has a certain attraction for itself, and water has a certain attraction for itself. But when you put the two together, their interaction is very strong. Water's like this, right? And it's polar in that direction. And acetone is like this. I think that's acetone. Yeah. So it's polar like this, and they're very, very strongly attracted to one another. That gives you the concave deviation because of this very strong interaction at this level. Ethanol and hexane. Ethanol has the potential for hydrogen bonding right there. Okay, so it's a strong interaction between the ethanol molecules, but what's the other one? Hexane. Hexane is, well, I'll just put the empirical form, the molecular formula. 14. That's hexane, C6H14, and it's a non-polar. So the interactions are very weak. The interactions here are not as strong as water, but they have some interaction. But then when you put them together, while they are soluble to a certain extent, right, they don't interact very well. Right? So it tends to give you the convex deviation. Oh, we got to figure this one out. All right. Which one of these is ideal? Which one's positive deviation and which one's negative? All right. So what we need is, let's see, which ones would be strongly attracted to one another? I think ethyl alcohol and water, because they both have hydrogen bonding. So they would be very strongly attracted to one another, as opposed to the water by itself and the ethanol by itself. Whereas, let's see, does that give us answers, or we have to just have to assume that I'm right? I guess so. Hexane and chloroform. Right? Hexane and chloroform tend to be repel one another. They would produce a convex deviation. And hexane and octane, actually, hexane and octane should be about the same. Right? They're both hydrocarbons, non-polar. So the attraction before and after formation of the solution is about the same. So that would be an ideal. C would be the ideal. Okay. Anybody want to argue? Okay. What's a colligative property? That's a big word. Let's erase that. Erase this. I'm not exactly sure what words colligative is derived from. I'm sure it's either Latin or Greek. But basically what it means is that the property that you're measuring, whether it's boiling point elevation, freezing point depression, osmotic pressure, or vapor pressure, these values, these measured properties only vary for solutions, only vary with the amount of the solute in solution. It doesn't matter what the solute is. It matters what the solvent is, but it doesn't matter what the solute is. That's a colligative property. Boiling point elevation. Everybody knows that when you put antifreeze in your radiator, along with water, mix them in there, one of the things it does is it keeps your engine boiling over in the summer because the boiling point of that solution is much higher than water. Okay. Similarly, freezing point depression. The antifreeze in your engine also prevents your engine block from freezing and cracking in the winter because the freezing point of the ethylene glycol solution is much, much, much lower than water. And you could get the same effect with sugar or salt. If you have the same number of moles as you would with using ethylene glycol, then you would get the same effect of boiling point elevation or freezing point depression. Now, there are other factors not to use them. One is salt would be corrosive in your engine, right? Sugar would may ignite or gum up, right? It would change. Ethylene glycol is fairly stable at a range of temperatures, so that's why we use that instead. But the effect it has on those two values only depends on the amount of ethylene glycol in the solution. You could do the same thing with anything else. As long as it's soluble in water and you can get the same number of moles per liter. Well, actually, when we're working with boiling point elevation, freezing point depression, we're using moles per kilogram, not moles per liter. Osmotic pressure. What's osmotic pressure? I think we have some slides on that, don't we? Yeah, okay. So I'll talk about osmotic pressure when we get there in a minute. But if you've had any biology courses, ultimately they talk about osmosis, right? The movement of water through a semi-permeable membrane. Builds up pressure on one side or the other, depending on the relative concentrations on either side of the membrane. So you've heard of hypotonic and hypertonic, isotonic. Okay, we'll cover that in just a minute. Vapor pressure. The vapor pressure of the solution depends only upon the concentration of the solute. The vapor pressure will be depressed as the concentration of solute goes higher, but it only depends on the number of moles of the solute, not on what the solute is. Okay, those are all colligative properties because it doesn't matter what the solute is. Boiling point elevation. All right, so the formula that controls or that determines that change in temperature, your boiling point is elevated by that much. So if you're talking about water, it would go from like 100 degrees, it might go up to 101, 102, 103, 140, whatever. Depends upon a proportionality constant, which is characteristic of the solvent. So with a different solvent, there will be a different K. But then over here, you have the molality of the solute. Okay. So how would you apply this? If you measure the boiling point of the pure solvent, get a value, then you dissolve a certain amount of solute in it, you get a different value. What's the difference between the two? And in this case, for this one and the next one, we're only interested in the absolute change. Boiling point elevation, that's a positive move. Okay, so that one's easy. But freezing point depression gets more negative. So typically what you would say is final temperature minus initial temperature will give you a negative number, but we don't want that. We only want the absolute difference. So in this case, you need to know that. You need to know this measurement, pure versus solution. Then you can calculate what's the molality of the solution. And it doesn't matter what the substance is. This will tell you what is the molality of that solution. So this is one of the ways. Remember when we did empirical formula calculations and then we went from there to molecular formula? You don't remember that. We had to know what is the molar mass of the molecule and compare that to the empirical mass that we calculated from percent composition. How did they get that value? If you don't know what the molecule is, how do you get it? This is one of the ways to get it, because this tells you how many moles of that substance are in the solution. And if you know the mass that you put in the first time, you got moles, you got mass, you can calculate the molar mass using this method. We're going to do that next week, only not with this one. We're going to use freezing point depression. So we have a different K, K freezing, than we do K boiling. We're going to use lauric acid as our solvent. It's a fatty acid. And the solute is going to be benzoic acid. And we're going to calculate the molar mass of benzoic acid based upon its effect on the freezing point. Okay. That's the next slide. There we go. So you have to be given these values right here. There's no way to determine those. They have to be given to you. And it should be in the method. And then you're going to run the experiment with pure solvent first, the lauric acid, and then you're going to just dissolve in it a given amount, mass of benzoic acid, and then calculate the number of moles of the solute that correspond to that mass, calculate the molar mass. This graph shows where the freezing point depression and boiling point elevation come from. The red lines on this phase diagram give us the vapor pressure of pure water. So we're talking about that phase line. Well, let me use this. The phase line right here, right? This is the liquid area of the phase diagram. This is the gas area, and this is the solid area. Okay, so this phase line is the difference between liquid and gas. So the vapor pressure of water shifts up to this position for this, that's pure water. The solution shifts to this blue line. And the that's boiling point. Freezing point is this one between liquid and solid. So this is the pure substance and this is the solution. So when we draw all these together, and actually you can determine this for this colligative property for a sublimation line too, right, between solid and gas. Right, so they've done that already. And apparently it does affect it a little bit. But the difference here, freezing point of water versus freezing point of solution, is where they get this difference. And then the boiling point difference is between these two lines. Okay, let's see. How are we doing on time? 2:30? We're given 25 grams of glucose with 180.16 grams per mole. This is the solute. And we calculated from that we have 0.13877 moles of glucose. So by definition, we need moles of glucose divided by kilograms of solvent. The solvent is 200 grams of water, which is 0.2 kilograms. That gives us 0.694 molal. So we take the formula here, and this is the K value for the boiling point elevation for water. degrees C per molal. And this is the molality of water. This is the difference in temperature from pure water to the solution. So the boiling point of water is 100.35. And that's what we get right here. All right. I got lots of flies in the ointment. Here's another fly in the ointment. Notice that glucose is the same when you put it into water as it was before you put it into water. It didn't change at all. And what I'm talking about is it did not dissociate. It didn't break apart. But many of the salts that you put in water, acids and bases too, when you put them in water, they break apart. So if you put 1 mole of a salt like sodium chloride into solution, what you actually have in solution is 2 moles of particles, sodium ions and chloride ions. So that's what this Van Hoff correction factor is, the I. And basically what we're saying is that sodium chloride in aqueous solution is not that. It's actually this. So for every mole of this one, you get 2 moles of ions. And remember, colligative properties don't care what they are. We just need to know how many moles there are. So if we're saying we have a molal solution of this, we actually have a 2 molal solution of ions. So the Van Hoff correction factor is the ratio of this to that. So this is 2 to 1. Van Hoff for sodium chloride would be 2. And you would just insert that into this calculation here as an I. Like that. So in this case, it would just be 1 for glucose, because glucose does not dissociate. Now, corollary to the fly in the ointment. As the concentration of your ions increases in solution, the probability of forming ion pairs where they actually do this, they go back to that in solution, increases. So the higher the concentration, the more likely you are to get some of the sodium chloride ions to actually associate with one another. It may not last for very long, but on average, it produces a concentration, a molal concentration of this compound somewhere in between the two. Instead of 1 here and 2 there, it might be 1.8 or 1.9. So, and the only way that you can tell that is to do the experiments and calculate it based upon this formula. You calculate what the I is for every concentration in a series, and then you draw a curve, and you know if your concentration is in this range, the I is going to be a certain number. All right, so it's like looking it up in a table. That's ion pairing. But theoretically, and with weak solutions, very dilute solutions of these salts, this works. So this would be I equals 2. Potassium nitrate, I equals 2. Let's see, calcium chloride, I equals 3. Let's see, our example there is sodium phosphate. This dissociates into 3 sodium ions and 1 phosphate polyatomic ion. So that I would be 4. Okay. All right, I didn't give you the whole story. Concentrated solutions, yes. Ion pairing is more of a factor. Ion pairing is also more important for highly charged ions, those that have very high charges. So I would think this one, being a 3-, would be more likely to ion pair with sodium than these would. Well, this more than that, and that more than this, because that's a 2+ charge. So what it could actually do is you could just get one phosphate pairing with one sodium, and that would reduce the I by a little bit. So there's your modified equation. And that works for either one of those. Okay, now I'm kind of gun shy because I don't want to linger too long because it might cut me off again. But those are the breaks. Let's try this one and see if we can make sense of it. Let's see. I'll leave those two up there because it looks like this might be needing it. You take 20 grams of sucrose. Oh, I think this one also has worked out, isn't it? Yeah, this one's worked out, so I don't have to draw it on the board. But we can extract information from it. Let's do that first. 20 grams of sucrose. And sodium chloride. So it's a mixture, but we don't know what the composition is. There's 20 grams of that. Is mixed in 1 liter of water. That's the solvent. And they both go into solution, right? They're very soluble. The freezing point of the solution is found to be negative 0.426. So the change in freezing point is negative 0.426 degrees C. Now we're only going to be interested in the absolute, right? When we put it in the formula. So we drop the sign. Assuming ideal behavior, we want to calculate the mass percent in the original solution of sucrose and the mole fraction of sucrose in the original mixture. Okay, so here's the way it goes. We're going to have to use a little algebra. We'll create an unknown. Come on, keep going. There we go. So those first few lines we have, and we also have calculated the molar mass of sucrose. Or was that one of the? No, it wasn't given. We have to look it up or calculate it. Sucrose. So the molar mass of sucrose is 342.34. That's a lot. It's a big molecule. Okay, here's what we're saying. If we're going to calculate the number of moles of sucrose, then we need to know the mass of sucrose and divide it by the molar mass. Correct? So we're saying X is equal to the mass of sucrose. Now, why did we choose X for sucrose? Because it asks us for the mass percent of sucrose. And that's one of our unknowns. So the mass of sodium chloride then would be 20 minus X. Okay. So far, so good. That means the moles of sodium chloride would be 20 minus X divided by 58.45, because the molecular weight of sodium chloride is 58.45 grams per mole. And you calculate that also from periodic table. Okay, the molality of the solution then is the moles of sucrose plus the moles of sodium chloride divided by 1 kilogram. Right. 1 liter of water is 1 kilogram of water. Okay, so that's as far as we can go on this slide. Now what we have to consider is that sucrose does not dissociate, sodium chloride does. So the correction factor for sucrose is 1, I equals 1, and sodium chloride, I equals 2. And the freezing point depression is this value right here, that K value. But we don't know what this is. We know what it is for each individual, but we don't know what it is for the total. All right, so the change in temperature is 0.426 degrees. So we know that goes here, 0.426. And we know that we're going to have a correction factor, I, because sodium chloride does dissociate. We just don't know how much it is. And we're saying that the molality of the solution is a combination of the 2 molalities that we've calculated, or we've created formulas for the molality for each sodium chloride and sucrose. So what we're going to do is we're going to say this second formula, where 1 times x over 342.34 plus 2 times 20 minus x over 58.45 is equal to I times m. So where do we get 0.2290? We solved that formula. The first formula on that list, we solved it for Im. Right? And we know that Im is equal to the I times the molality is equal to the expression on the left. So now we set those equal to each other and solve for x. And that's what we're doing step by step. And we find that x is equal to 14.55 grams of sucrose. That means what's left over, 5.45, is sodium chloride. Now we can calculate the mass percent, because we know the total, 72.8% sucrose, and the remainder is sodium chloride. Mole fraction, we have to actually go in and take the masses, take the, calculate the moles of each one. So the moles of sucrose is the mass divided by its molar mass, and then the total moles here. And we find that it's 0.31 mole fraction for sucrose. There's a lot of algebra in there. I'm not going to have you do one of those on a test. That would take too long. Take half an hour to do that one, probably. Okay. This one, I think, gets ahead of itself, because what we're talking about here is hypotonic versus hypertonic solutions. And what we're going to do is use the freezing point depression to tell us what is the molal concentration of the solution outside the cell. We know that inside the cell it's given as 1/4 of a molal is inside the cell. So we need to calculate outside the cell and compare the two and see which way is the water going to move. Okay. So those are particulars, and this is the calculation for what's the molality of the solution. Right? We determine from this formula that the molality of the solution is 0.132, but the molality inside the cell is 0.25. So which way is the water going to move? It's going to go from the hypotonic outside inside the cell, and the cell will rupture eventually. Okay. Now, how do we calculate osmotic pressure? We were using osmotic pressure in conjunction, oh, I shouldn't have done that, in conjunction with the colligative property of freezing point depression. But we didn't really define what the osmotic pressure was. The osmotic pressure is measured against the flow of a solvent into the solution through a semi-permeable membrane. So basically, actually a picture makes more sense. The formula, let me write the formula so I can get off of this slide. We use pi as the osmotic pressure. That's our representative there. And then we have molarity, gas constant, and temperature. Okay. In this case, temperature is going to be Kelvin. Why? Because we're using a gas constant. So it has to be Kelvin. And we're talking about pressure. So we're going to use this gas constant is going to be the one with atmospheres in it, 0.08206 liter atmospheres per mole K. All right. So those are the variables in that formula. All right. So let's see if we can get a handle. That's kind of a small picture. Pressure, osmotic pressure, is measured as the difference between the surfaces of the two, the liquid on the outside of the container, and once it reaches equilibrium, how high is the solution inside the container. The difference between the two is that pure solvent, usually water, outside the container, and then inside the container is a solution. So we know that the water is going to be hypotonic to the solution inside and move into the solution. So when we express osmotic pressure, we're talking about the osmotic pressure as compared, comparing the level here versus the level there. Now, why does it stop? Why didn't you just keep going? Because at the molecular level, there's competition between water moving in through the membrane and water moving out through the membrane. There's an equilibrium that is eventually established. On the molecular level, as the level of the liquid rises inside the tube, then it's bearing down with more pressure. And that pressure is driving more water molecules through the membrane this direction than it was when it was sitting still and nothing was happening at the very beginning. So as we build up this pressure, now we're driving water molecules back through the membrane at the same rate as they're entering the solution. So that buildup of pressure is what is established equilibrium in the movement of water across the membrane. We know that's true because reverse osmosis works. You can take a concentrated salt solution, a brine or ocean water, and run it through a semi-permeable membrane under high pressure, and it will transfer water through that membrane to the outside of the membrane and leave the salt inside. And that's one way that some countries and some localities purify water for drinking purposes and for other things, reverse osmosis. So you increase the pressure so high, it exceeds the osmotic pressure of the salt solution inside and starts driving water back the other direction. There are some cities in California that do that. They're probably not going to be able to for very long because it takes a lot of energy to do that. And they don't have enough electricity over there, and gas prices are too high. So, you know, California is just up the creek. up the creek of their own making. Let me put it that way. This is another way to look at osmotic pressure. If you have a solution on two sides, this U-tube with a membrane in between, you see the same movement, water moving from the left-hand side into the right-hand side until the difference in pressure is such that you have established equilibrium of movement of water through the membrane. Okay. Oh, you can use molar mass. You can use osmotic pressure to determine the molar mass of a compound. Let's see, is that one worked out, or do I need to do that one? Oh, okay. Yeah, it's worked out on the slide, so I don't have to write it. So we have 33.4 milligrams of compound dissolved in 10 milliliters of water at 25 degrees C. Right? We have to take account of the temperature. So that's why, since temperature is here, we can use, well, no, that's not true. Temperature is being compensated for here with the gas constant. So we don't have to use molality, we can use molarity. The solution has an osmotic pressure of 558 torr. Calculate the molar mass. Okay, so these are the values that are given. And we need to calculate osmotic pressure. So, since this value is 0.08206 liter atmospheres per mole K, our pressure needs to be in units of atmospheres. So that osmotic pressure in terms of atmospheres, we have to change 588 torr to atmospheres, which means we divide it by 760. So that 760 goes on this side of the equation, and then we fill in the others. We don't know molarity, but we do know this constant and that temperature. So we plug those in, and we find that the molarity of the solution is 3.164 times 10 to the minus 2 moles per liter. Right? That's first step. We know the molarity of the solution. Now, how much of the solution do we have? Well, in the previous slide, we have 10 milliliters. Right? And 10 milliliters is 0.01 liters. So we know the concentration. We know the volume. We can calculate, since molarity equals moles per unit volume. If we want to know how many moles that represents, it's molarity times volume. So that's why we multiply 3.164 times 10 to the minus 2 times 0.01, and we get 3.164 times 10 to the minus 4th moles of the compound. And we also know how much it weighs, right? That was given to us here. 33.4 milligrams of compound is dissolved in 10 milliliters of water. So 33.4 milligrams is 0.0334 grams. And we know how many moles that represents. We calculated the molar mass, grams per mole, 106 grams per mole for that compound. And we don't have to know what the compound is at all. That's one way to find that molar mass that we used in calculating the molecular formula last semester. Okay, I like this one. Have you ever wondered? I used to wonder as a kid. I'd never seen a sequoia before, but I had seen some pretty tall trees. And as I got older, I got more information through my science courses. And I found that trees that were more than 33 feet tall could not, you couldn't push water up to the top of that tree any taller. Because if you make a barometer with water instead of mercury, and you evacuate the top of the tube like you do with mercury, the water will only rise to 33 feet. That's 1 atmosphere. So every scuba diver will tell you, for every 33 feet you go down in the ocean, you add another atmosphere of pressure on your body. Okay, so how do we get a tree that's 100 meters tall to get water to the top? That's a sequoia, or any tree that's taller than 33 feet. All right, that's about a little over 9 meters. Well, there was one proposal years ago that said the water is sucked up, right? Under each of the leaves in any tree, there are little tiny holes in it called spicules, and they're controlled. They're open and closed by guard cells. So when those guard cells open, water evaporates. And the theory was that as the water evaporated, it produced through surface tension a pull on the water that would pull it up the tree. But some research was done on that and said there's not enough force to pull water up that high. Right? So we had to throw that idea out. But here's another idea. Suppose we measure the osmotic pressure of the sap in the roots. Okay? The concentration, the molar concentration of dissolved substances in the sap of the roots is much, much higher than it is in the groundwater outside the roots. In fact, it's been measured. The osmotic pressure in the tree's roots is 20 atmospheres. That's pretty big. That's pretty high. Is that enough pressure to drive water to the top of this sequoia? Okay, here's what we're going to do. How high is 300 feet in millimeters? With dimensional analysis. So we convert 300 feet to 9.144 times 10 to the 4th millimeters is how high that water has to rise. Minimum. Okay. How high does 20 atmospheres push the water? Well, we convert 20 atmospheres to millimeters of water. We know 760 millimeters of mercury is 1 atmosphere. So we convert millimeters of mercury to millimeters of water using the density, the specific gravity of mercury, 13.56 millimeters of water for every millimeter of mercury. That's because mercury is 13.5 times denser than water. So with that conversion, we find that 20 atmospheres will push water 10 to the 5th millimeters high. But it only has to go just short of that, 9 times 10 to the 4th. So yeah, osmotic pressure in the roots of the plant will push water high enough to go 300 feet in a tree. I thought that was cool. Yeah, just a few more slides and we'll be done. Done with this. A suspension of tiny particles in some medium, but not a solution, a suspension. If the particles are small enough, they will remain suspended indefinitely. Okay, that's a colloid. It's not a solution, it's a suspension. And it's based upon particle size. So you make the particles small enough, then they will remain suspended simply because of the kinetic energy and the impacts from the solvent. Right? You got all these solvent molecules, they're vibrating and they're traveling and they're bouncing off everything. There's enough kinetic energy there to keep the small particles suspended. So examples of a colloid. You ever eat Jell-O? It's a colloid. Okay. You ever get lost in the fog or smog, either one? That's a colloid. Fog is a liquid suspended in air, gas. Smog is more particulate, like smoke particles suspended in air. But it stays there because their particles are small enough. Okay, here are other types of colloids. I mentioned the fog, aerosol sprays, smoke, airborne bacteria, they're colloids too, in gas, solid in gas. Whipped cream is a gas in a liquid. And we can't say solvent and solute. If I did, that was a mistake. We have to say dispersing medium and dispersed substance, because it's not a solution. Solvent and solute is reserved for definitions of solutions. So the dispersing medium is the major component, like milk and mayonnaise. That's a liquid in a liquid, usually fat in the water. So how do we get milk? You've heard of homogenization? Homogenization is a process where you make the fat particles in milk so small they don't separate, right? You don't make cream out of them. I can remember as a kid, the milkman coming by the house, and he'd drop off 2, 3, 4 quarts of milk and go on. And if you left it out there long enough, you start to see cream on it, right? It was not homogenized. But homogenization is a very simple process. All you do is take the milk and put it under enormous pressure, 100 atmospheres, and drive it through a sieve with very small holes. And in order to get through the sieve, the fats have to be broken into very small particles. Other examples, paints, clays, gelatins, those are solids dispersed in a liquid. Oh, I like cheese and butter. That's liquid in a solid. And ruby glass is a solid in a solid. And each one of these has names, right? Liquids and solids dispersed in a gas, they're called aerosols. A gas dispersed in a liquid is a foam. A liquid in a liquid is emulsion, right? And mayonnaise is a colloid. It's also named an emulsion. And we use emulsifiers to help suspend those small particles. And one of the emulsifiers is egg whites. So mayonnaise has to have egg. In fact, mayonnaise has a standard of identity. For the Food and Drug Administration says, if you call it mayonnaise, it has to have these components. If it doesn't, can't call it mayonnaise. You have to call it salad dressing. A sol is a solid in a liquid. Gelatin, like Jello, clays and paints. And you can, a gas in a solid, you can make a solid foam. How about the ceramic bricks on the space shuttle that covered the surface of the space shuttle? Right, those are solid foams. They were mostly gas. In fact, you could pick them up, I mean, no effort at all. They were just light as a feather. Okay. So what do we mean by coagulation? Coagulation occurs when the colloid is destroyed. When the dispersed substance becomes too large and drops out of suspension. So you can see that with, well, we normally think of coagulation in terms of proteins. Like when you fry an egg, right? The egg goes from liquid to solid because the proteins in there under that heat, intense heat, rearrange and become too big to be suspended. But we used to use coagulation in the lab and in the purification process. Actually, a better example would be what happens to blood when it sits out like that in the air or at room temperature. Eventually, it'll coagulate, separate. The proteins in there that were once suspended in the colloid, now rearranged to make bigger size groups, particles, and they drop out. And what do you have left? Plasma. And it's usually accomplished if you force a colloid to coagulate. Usually you can do it by heating. I mentioned that one before, but you can do it also by adding electrolytes. So the electrolytes take colloids that are especially have charges on them, will cause them to clump together. And that makes the size of the particles too big and they drop out. Sometimes we call it salting out. Oops, that's it.